My efforts to record yesterday failed, or Friday, not yesterday, failed. So we're gonna get it this time. But before we start, before we go over what we got for the bell work, I wanted to open the floor to you guys. Do we have anything good that happened over the weekend? Anything that they're excited about that's coming up this week? Yeah. Oh, super exciting. What kind of puppy?
A black
Black lab, that's adorable. Name? Are you still deciding on
I think
names?
we're gonna go with cat.
Cat, that's a good name.
That's a good
That's a good name. That's adorable. That's fantastic. Does she live close by? Do you get to
Yeah.
visit this puppy a lot?
Yes.
Are you gonna be like there just all the time, hang out with them?
Totally.
That's so wonderful. As soon as, okay, I love my cat. Cat is wonderful. But as soon as we have either enough space or if the cat, disappears from the equation, which probably won't happen. I believe he's immortal. I don't think he's ever going to die. But I'm looking forward to getting a puppy. I love the cat. I love the cat. The cat would murder a puppy. The cat would not get away. He does not tolerate other life. Like 15. Like the cat would not do well with a puppy. So if we got a bigger house and the cat was able to be like in one part of the house and the puppy was able to be in another, that would be totally fine. That'd be great. And that'll be what happens. We'll see. Oh yeah. Yeah. On the internet forever, in case my wife needs proof that something nefarious happened to her. No, cat is wonderful. He's pretty evil, but I'm excited about a puppy in the hopefully not so distant future. So my family always grew up with Shelties. Shelties are pretty loud. They are like border collies, but kind of smaller. And so they had three. And one of them was great. He passed away recently. And the other two were less than great. And one of the three was absolutely terrible and has made it so that my wife is like, we're never getting a Sheltie. And I'm like, they're not all like Cece, but it's fair. I understand. Super fair. So I don't know, some kind of like ideally we'd probably adopt, but like if we're talking about breeds like golden retrievers would be like a nice, safe, like family kind of pet. Could be nice. So loud. So loud. Her job was let me sit on the stairs and look out the door. And if like you walk in, it's like, oh, that's adorable. She's just like perched on the stairs. Anything that moves, 5 minutes of nonstop barking, uninterrupted barking, high pitched, awful. At nothing. It would be like if she thought something moved. It'd be like a leaf would blow by, or an imaginary leaf would blow by, and it would set her off for 5 minutes. It's the worst. Yeah, not my favorite. Very bad. She was also really stupid. That was dumb dog. That was dumb dog.
That was the dog stupid.
Do you not remember the story of like we put her on the raft and like the first thing she did was like step off into the water and just like no attempt to swim, just like sank to the bottom. And so we're like freaking out. We like scoop her out of the water. This is like as a puppy. We put her back on this raft. The second thing she does on the raft is step off the raft into the water and just sinks. It's like goodness, dog. Yeah. But unfortunate. That's my good thing is that I don't get to hear Cece's barking all the time. Yeah, it's rough. But yeah, that's probably no shelter. All right, let's take a look at what we've got here. First thing that I want to do, and I'm always going to want to do this, and actually for this question, we're really going to see the payoff behind why I'm having us do this over and over again. I want to write the piecewise definition of this function. Oftentimes the piecewise definition has just kind of been like, it's there and we don't really use it. It's like a quick check of like, do these answers make sense? This is an example of a problem where it's actually pretty important to understand what our function is claiming. You also can, if you want to, memorize the greater than and the less than, if that is your preferred approach. I am not going to tell you not to do that. I'm saying, though, that we do not need to do that if we use the piecewise definition. All right. So whenever we're talking about the piecewise definition of the function, I am not yet looking at the less than or equal to 4. I am focusing solely on the absolute value. So what are the two different things that my absolute value can do? So either it's going to stay the same, like keep a positive, or it's going to turn a negative positive. And how do we accomplish that? What's like our go-to way? Multiplying by -1. So we are either going to stay the same, or we are going to multiply by -1. What's going to stay the same? Like if I take the absolute value of 7, what stays the same? 7 stays the same. It's the inside of the absolute value that we're talking about that's staying the same. Okay. And what are we going to multiply by -1? Like if I take the absolute value of -7, what are we multiplying by -1? Again, the inside of our absolute value. Right? So we're not talking about x, not talking about anything other than whatever the entire inside of this function is. That is what we are going to be working around. Okay. And what was the condition we said? When are we going to stay the same? Positive, we're going to stay the same. Negative, we're going to switch. What is the mathy way to say that we want to be positive? Greater than 0. So maybe we say like we want the inside of our function or of our absolute value to be greater than 0. And then what would negative look like? Less than 0. Now, positive and negative are great. What's the third option for what our number could be? Positive, negative, or 0 itself, right? Which is kind of neither positive nor negative. Does it matter which definition we apply to 0? Like if I take the absolute value of 0, could I get to the right answer by leaving it alone or by multiplying it by -1? It doesn't really matter, right? 0 times -1 is 0. 0 left alone is also 0. So it doesn't matter which definition we apply for 0, just pick one and run with it. I'm going to pick the greater than. Doesn't matter. You can pick either. Could you do both? Sure. It's kind of bad practice, so I do not want to encourage you to do that. All right. Again, I want to clarify what stay the same means. What's going to happen to 3 minus x if we are staying the same? It's going to stay 3 minus x. We leave it alone. 3 minus x just stays 3 minus x. Now notice here, 3 minus x, the x does not become positive. It's not like we turn into 3 plus x. It's not what absolute value is, right? 3 minus x, is this a positive number or a negative number? Do we know? We have no idea. It's going to depend, right? If I plug in -1,000 here, I'm going to get a really big positive number. If I plugged in positive 1,000, I'm going to get a really big negative number. It depends on the value of x. Absolute value only makes that change after all of the kind of internal processing gets done. And then likewise, multiplying by -1, you don't have to write it like this, but I really like to include where this is coming from. We are taking the inside and multiplying it by -1. Right? Literally multiplying the inside of our absolute. Yes. Absolutely, you totally can. Totally you can simplify. I'm not simplifying just so you can kind of see where each of the pieces plugs in. I don't want to link. But absolutely, if you wrote this as -3 plus x, perfect. I'm taking advantage of the fact that I don't require us to simplify to make it more obvious, like where all this stuff comes from. All right. Now, the other thing that I want to clean up here, I don't love that my conditions aren't in terms of x, right? When 3 minus x is greater than or equal to 0, cool, but like what values is that actually talking about? All right, I listed 2 of them that I just pulled out of thin air, right? Negative 1,000 and 1,000. But where does that actually start to take place? Solve this equation for x, what would you guys do? Divide by -1. What's going to happen when we divide by -1? The greater than sign becomes a less than sign. Did you guys get that x must be less than or equal to 3? Notice that the 4 we have not yet brought the 4 into the fold. Right. Likewise, what did we get when we, exact same thing, right? Subtract 3, divide by -1. What did you guys get? X is greater than -3. Oh, we haven't solved yet. This is just the conditions. Yeah. So if x is less than or equal to 3, sorry, that's not -3, that should be +3. If x is less than or equal to +3, we're going to use the leave it alone definition. And if we are greater than 3, then we are going to use the multiply by -1 definition. This is just setup, right? We haven't even talked about what's going on here. This is the piecewise definition. If hypothetically, on a test that you had on, I don't know, like Wednesday of this week or something, if on number 6, part A, it asked you to write the piecewise definition, this is what it's asking you to do. Hypothetically. Yeah. Kidding, sorry. So whenever you multiply across, so imagine subtracting 3, you get -x is less than -3. And then multiplying or dividing by -1 on both sides, you get x is the less than becomes a greater than +3. So -x is less than -3, and then dividing by -1, x is greater than 3. Yeah, okay. Right, the piecewise, this is the piecewise definition. If it asks you what is the piecewise definition of your absolute value function, this is the piecewise definition. Yeah, whole thing, that entire thing would be your answer. Yep, the whole, yeah, this whole thing. And honestly, I would use the blue instead of the unsimplified. It'll make your life easier, right? That whole thing would be your answer. Yeah. Yeah, so Emily has a really good question here, you guys. Emily has a really good question here. Emily's question was, does the stay the same definition always go with the greater than? Does the become negative definition always go with the less than? For this original setup, yes. But notice that for our final answer, for what x is relative to, it can switch. And it will switch when the x has a negative coefficient. So notice how we started as a greater than, but then became less than. That's because the negative coefficient for things. If it had been x minus 3 instead of 3 minus x, this would have stayed a greater than sign. But it's because we're staying the same when we are positive, and to be positive means to be greater.
So the unsimplified would always stay.
Yeah, the unsimplified haven't solved for x will always be greater than to staying the same, less than to multiplying by -1. Yeah, really good question. But again, note, when you solve for x, that is not always a given. Not always a given. Yeah. Yeah, if x is 7, then we are adhering to the x being greater than 3. And so we're going to use the multiply by -1 definition. So what happens when we plug 7 into x? It becomes -4. What's the absolute value of -4? +4. So notice there what absolute value did, it flipped us. Right. So when x was a positive number for a particular size, bigger than 3, it's doing that flip definition because we're subtracting a large positive number. Yeah, good question. And vice versa, if we were a negative number, bigger than, or a number that is smaller than 3, right? Less than 3, then we're going to be employing the leave alone definition. Always with absolute value. This is we've got our piecewise definition. Now we go on to solving. Always with absolute value. There are 2 equations that we need to solve. We have 2 different definitions here, right? Sometimes we stay the same, sometimes we multiply by -1. We are always solving 2 equations. What is one of the equations that we are going to be solving? Fantastic. So the leave it alone problem is going to be 3 minus x is less than or equal to 4. When are we allowed to do this? What is the condition that x must satisfy for us to be solving this equation? It must be less than or equal to 3. So we can only use this equation as long as our x is staying less than or equal to 3. We're going to see that come back into play here momentarily. What is the multiply by -1 equation that we are going to solve? -3 plus x is less than or equal to 4. Notice here, you can just kind of copy and paste this if you want to, but what Sophie has done is she's distributed the -1 through the parentheses. Totally fine to do. That's great. Love it. And now we are going to solve each one. All right, what would you guys do to solve the left-hand equation? Love it. Yep. What happens when I divide by -1? We flip the inequality, greater than or equal to -1. Fantastic. And then on the other side, what are we going to do? Okay, that one was nice. Didn't even need to do a division step. All right, am I done? Yeah, we got to check our answers here. Okay, let's check our solutions. Right. So when we are staying the same, we find solutions where x is greater than or equal to -1. Are we allowed to include all values of x that are greater than or equal to -1? Or do we have to cut off somewhere? When does this definition stop applying? When are we not allowed to stay the same? At 3. For instance, would +4 be a valid solution for x being greater than or equal to -1? Yes, it would be good for this, but no, because we can't use that function for, right? So we couldn't use +4 specifically because it just doesn't match with the definition that we're claiming that that's. At the very least, we couldn't use it here. Right. So what is the smallest possible value of x that we could start with? So from -1, and then what's the largest possible value of x that we could get from this definition? Up to 3. If I go higher than 3, it's not like my equation is giving me a problem. The problem I'm running into is just from our setup. I'm not allowed to use this equation for any x value that is bigger than 3. You just can't use it. All right. What about on the other side? We said we want to be less than 7. Does that mean I can use like -14 as one of my solutions for my second equation? What's my cutoff? How small am I allowed to go for my second equation here? I have to stop at 3. Right? So, yeah, why do we have to stop at 3? Where is that coming from? That was coming from this condition that we observed right at the start. So remember when I said the piecewise definition was about to be useful? Here it is being useful. Yeah. At some point we divided by -1, subtracted 3.
If x is greater than 3, and then you wrote it out, it's less than.
Oh, I'm just solving this equation. So the less than from here is just coming from here. What is the that? What don't we use?
We don't use x is greater than 3.
We are currently using x is greater than 3.
Like when you're solving it.
No, not when we're solving it. No, we're using it now for when we are checking to see which solutions we are allowed to keep. Right? So this is saying we want all of these x values that are less than or equal to 7. Right? But this tells us that we can only do those x values up to 3. Right? So we can have 7, we can have 6, we can have 5, we can have all the stuff that kind of fills in the gaps. But right when we get to 3, we're cut off because we stop being allowed to use this definition. Does that make sense of how we're using the x is greater than 3 condition to like check? Because essentially, think of like we've got this number line. Got 3. Say this is what, -1, and this is 7. We're saying we can use one definition from 3 and above. We're saying we can use another definition 3 and below. And it's all below, right? We can go all the way down. And from 1, using this definition, we say, oh, I want everything to the right of 1, but I'm not allowed to use that definition past 3. Here, I'm saying I want everything to the left of 7, but again, I'm not allowed to use that definition as soon as I get to the left of 3. So this 3 is acting like the cutoff point on both sides. So what is the smallest value that I would be allowed to include in my interval here? Or what really, rather than what's the smallest, because we can't actually pin that down. What is this interval going to look like? From what value to what value? From 3 to 7, including the 7. Importantly here, just with the definition we've written, not including the 3, not because, again, it's necessarily wrong, but just because we said that it was strictly greater than 3 there. Yeah. Okay. Yeah, would it necessarily be wrong to include the bracket? No, it would just kind of be poor practice. Again, there's nothing wrong with that. Notice though that our solution already includes +3, right? We're saying we want to go from -1 to 3, including -1 and including 3. And then right after we've included 3, we're going to pick right back up and include everything to 7. The or equal to on the other equation? Absolutely. You could. Again, when I say that that's kind of poor form, the reason why is because if we're using a piece, and this gets a little bit above anything that we've really looked at in this class. If we used a piecewise function that is not, new word that you guys probably have a fairly good understanding of intuitively, a piecewise function that is not continuous at that kind of slope. So for instance, let's say I had a function like this, something like this, right? This is not a function because it's defined for both where this side ends and also where the side begins. And so if I asked you the question, well, what is f of, I don't know, we'll call this like -1, we run into the problem of, I don't know. And so generally you don't. Generally you say, oh, I'm either going to be on one side or the other. Now, the thing with our absolute value is that our absolute value is continuous, right? And so it's like, okay, am I using this point for my going down side, or am I using this point for the going up side? It doesn't really matter. And because it doesn't matter, you could do the inclusive inequality on both. And you'd run into that kind of weird issue where, like, I'd say that we're using 0, 0 as a point. And then I'd also say that we're using 0, 0 as a point, right? Like if I give you this and ask you, is it a function? Yes, we have a repeated value of x, but is there any ambiguity in where that value of x is going? No, both definitions agree that it is going to a particular point. And so we could include both. It's not wrong, it's just a little weird and a little awkward. So you would not be, I would not mark you off if you included both. And I would not mark you off if you said that was an inclusive 3 on that side, if that was consistent with what you had otherwise. Now, that being said, if we're talking about every number from -1 to 3, and then every number from 3 to 7, ultimately, what portion of the number line does that cover? Have we thrown away anything between -1 and 7 in what we're communicating here? No, right? We kept 3 for one definition. And so this is just everything from -1 to 7. Like we haven't actually tossed anything. -3, or rather the +3 was counted. Yeah, you can just say with -1. Question. There's a reason I wanted to go over this. Not in small part because, this on the test that we actually. But also just because I think that this is something that I think people really struggled with absolute value originally. And now we're throwing in this whole inequality business and all that. And also I think this really highlights well why we are doing this. Like it hasn't been particularly useful, I would say. Like there have been a couple of corner cases, like if I say the absolute value of something is equal to -1, sure, when I check those equations, I'll get that they don't work. But like, I could have just started with the problem and looked at that and said, oh, well, the absolute value of something is never going to be equal to -1, no solution. Right? There are shortcuts to each of those. And this one, there's not really a good shortcut. I mean, there are other ways to approach it, but I think that this kind of checking is very logically consistent. Yeah, I say. So the answer would be to the solution for this would be from -1 to 7. Why we needed to establish the piecewise function was to tell us when we stop with each of our animals, right? Otherwise, we'd just be taking everything that's less than, or that's more than -1, -1 to infinity. We'd be taking everything that's less than 7 to negative infinity, and who knows what we'd do. This gives us kind of our cut points. Like, hey, stop using this definition. Hey, stop using this definition. Yeah,
So
right.
the -1, 7 intervals.
Yeah, this is our final answer. And honestly, if you wanted to put it this way, I'm fine with that. I don't know. That's again a little bit awkward. It's not as simple as it could be, but I'm also fine. Either way.
Oh, wait.
These are cool.
Got the -1, 7. -1 stay side of the 7.
Yeah, exactly. Yeah, it's a combination of these two. And it just so happens that we don't skip any values between -1 and 7, so we can just say it for -1 and 7. Communicating thing. Good question. Other questions?
Which one's the step builder? That the,
I didn't use set builder notation here. Set builder notation, there are a couple of ways that you could communicate it. Kaylee did a really good job of communicating it in set builder. Or Kylie, sorry. It was all of the values of X where, and again, there are a couple of ways you could do this. I would say where we're between -1 and 7 is how I would personally do it. But there are multiple ways that you could do it. I would not use anything that you would not be able to use on, say, like the test. And since you will not have a graphing utility on the test, I would not recommend it. Good practice. This is in sports. This is in anything, right? You're gonna do the same in your competition the way you practiced it. Right. So if I practice my forehand in a way that's not very good, if I'm, hitting overheads from the baseline, then I'm going to do that in my matches. And that's not good. You don't want to build bad habits in your practice that then translate to bad habits when it counts. My dad would always yell at me about that. Not yell, he was very nice, but I like that. You shouldn't do that. All right, let's take a look at, I want to look at one more kind of subtype of problem. E and F are basically the same thing. The idea that we're trying to capture here is this inequality actually means something very fundamentally different when we are offsetting from a polynomial versus when we are offsetting from like an absolute value. So the actual kind of like interpretation piece, the solving here is a little bit different. But the logic of like, we're going to treat this like an equal sign and just run from there is very, very, very similar. So for instance, if I gave you x squared plus 3x equals -2, what would you guys do to solve for x? So this is kind of the key here. When we see a quadratic, the temptation should not be to like get one x on the other side, the other x on the other. It should not be to get x's on one side, not x's on the other side. It should be to offset from 0. And the reason why, and we're going to explore this really thoroughly in Unit 2, the reason why is as soon as we're offset from 0 and we factor, we can make a lot of really interesting claims. If we're not offset from 0 when we factor, we can't say as much. There's a lot, it becomes a lot less interesting. We need to be offset from 0. Okay, so looking at our original equation here, same logic, what would you guys do? Add 2 to each side. So what we're really going to solve here is x squared plus 3x plus 2 is less than 0. Now again, we've looked at this. What does it mean to be less than 0? This means negative. Okay. Now before, if it was equal to 0, we're going to factor it and we get like something times something equals 0. If I have a number times a number equals 0, what must be true about those numbers? At least one of them has to be 0. Now, instead of being equal to 0, we are claiming that it's negative. So if I have a number times a number and it's negative, what must be true about my two numbers? One is positive, one is negative. Perfect. If this were greater than 0, then what would I be looking for? 2 positives or 2 negatives. Right. Okay, so now we just need to factor this. Okay, that is maybe easier said than done. I tried to pick one that was fairly factorable. This is the whole like 2 numbers that multiply to make C that add up to make B. What are 2 numbers that multiply to make +2 that add to make +3? 2 and 1. And so then we could like split the 3x into like a 2x plus x. And then we could like, again, if this has been a while, we'll revisit all of this in unit 2. But I'm going to cheat a little bit. And we should get x plus 1. Actually, sorry, if I'm doing this in the right order, we should get x plus 2 times x plus 1 is less than 0. I got it from well, okay, I got it from somewhere else. What you would do is you would factor an x out from here, and then you'd factor an x plus 2 group out to the front. X times x plus 2 leaves behind an x. 1 times x plus 2 leaves behind a 1. X plus 2 times x plus 1. And we said in order to be negative, what needed to be true? 1 needed to be 1's positive, 1's negative. Okay, so now we just need to figure out when is that going to occur? When do we have where one of these is positive, one of them is negative? When do we switch from positive to negative? What value do we have to get through the zeros? So when would x plus 2 switch from being a negative number to a positive number? When is this 0? At negative 2. And then when would x plus 1 switch? At negative 1. Again, there are a couple of ways to go about doing this. I would just pick values and see what happens when you plug those values in, like nice, easy values. So for instance, what's a nice, easy value I could pick that's to the right of negative 1 that I could plug in here to see if I'm looking at positives or negatives? Yeah, 0 is nice and easy. What happens to x plus 2 when x is 0? Is it positive or negative? Positive. And what happens to x plus 1 when x is 0? Also positive. Okay. What's the value between, this one's maybe a little bit trickier. What's the value between negative 2 and negative 1 that we could check? Negative 1.5, sure. Negative 1.5 plus 2, is that going to be positive or negative? Positive. And then negative 1.5 plus 1, negative. Notice that x minus 1 switched from positive to negative. And then what's a nice easy value we could pick that's to the left of negative 2? Negative 3 is great. What happens to x plus 2 when x is negative 3? It's negative. And what happens to x plus 1 when x is negative 3? Also negative. And so where are we going to find the combination of having one value that's positive, one value that's negative? Between negative 2 and negative. And that's our solution. That's where we find our solutions. It's literally going to be from negative 2 to negative 1. Yeah, I see. What does less than 0 mean? That's why offsetting from 0 here is important. If it weren't offset from 0, we couldn't solve it. Yeah, Emily. Like for when they're both positive, both negative, things like that. So ultimately, what kind of number are we trying to make? A negative. And if I'm multiplying two numbers together, how can I do that and get a negative? Positive and a negative. So if it were greater than 0, where would we think? So let's do the exact same thing. Let's switch it though. Let's say that we're looking for what's going on when this is greater than 0. Where are we going to find it? two regions, right? Double negative. So that would be like to the left of -2. And or when they're both positive, that would be like to the right of -1. I could give you three numbers, right? How can I make positives and negatives with three numbers, right? We can either have all of them be positive, or two of them can be negative, one of them can be positive, or one of them could be negative, two of them could be positive, or all of them could be negative, negative. Right, so this is, think of the offset from zero as just telling you I need my product or my quotient, same thing, to be positive, or I need it to be negative. F is literally the same thing. Because two numbers multiplying together to make a positive versus multiplying together to make a negative, exact same logic here with the, right? A positive divided by a positive is a positive. A negative divided by a negative is a positive. So, exact same logic. We can. Do we want to do that real quick? Sure. I'm going to make a slight amendment to F. Let's make this greater than or equal to, just to add some spice. So the same logic, this one's actually already nice and packaged for you, right? You don't need to factor or anything. That's convenient. So we've got two numbers, in this case, multiplying together or dividing. Same operation. And the goal is to make a positive or to make zero. Let's focus on the positive bit first. When is my first number, when is my numerator going to be positive? When is it, or rather, when is it going to switch from positive to negative? At -7. And then where is my denominator going to switch from positive to negative? +2. Does that claim feel tenable? Does that feel good? Like, hey, when I pass through zero, I'm literally switching from positive to negative. So -7, our numerator is switching from positive to negative, and at +2, the denominator is switching from positive to negative. Yeah, green. Oh, you're good. Is that also just a resting? Yeah, you're good. You're good. Okay, let's pick representative values. What would be a nice, easy value for to the right of 2? To the right of 2? 3? 3 would be a good one. What's going to be true about our numerator when x is equal to 3? Positive. What's true about our denominator? Also positive. Okay. What's going to be true? Let's pick a representative value. What's nice and easy between -7 and 2? 1 would be easy. 0 might even be easier, but 1 is great. What happens to my numerator when x is 1? Greater than 0, positive. Okay. What happens to my denominator when x is 1? It's a negative. And then what about when I'm to the left of -7? What would be a nice, easy number? -8 is great. What happens to my numerator when x is -8? Negative, and my denominator is negative. And so what are the regions here where I'm going to be a positive number? Seven, 2. -7. Yeah, you're right. Okay. And what I have left off here is which ones we are allowed to include, because now it's okay to equal 0. Right? Before, if this had been an or equal to 0, we would have been allowed to include the -1, and we would have been allowed to include the -2, because multiplying by 0, that's great. Here, though, what do we want to be really, really careful about? There's actually a value of x that can never be a solution. 0 also isn't a solution, but there's something more fundamental that makes it so that this x can never be a solution. It's one of these two. I'll give you a hint. It's either -7 or it's 2. Why would you say 2? It's dividing by 0 rather than multiplying by 0, right? So if I'm just looking here, I'm like, okay, well, I'm going to include one of these because of the or equal to. Then the only one that we can include, you can only include zeros of the numerator rather than the denominator, right? So in this case, we would want to include the -7, and we would not want to include the 2 because 2 isn't a 0. 2 is a value that we are never allowed to be under any circumstances. Now, 2 was still important for us to figure out when are we switching from positive to negative. We just never settle it to, right? We can be 1.999999999. We can be 2.000000001. We just can't ever sit at 2. But exact same process. And in fact, this would look identical to x plus 7 times x minus 2 is greater than or equal to 0, except here we would be allowed to include 2 as a solution. So the only difference is that multiplying versus dividing, I can't include the zeros of my denominator as zeros of my inequality. Which should hopefully make sense. Dividing by 0 is not 0, right? It's closer to infinity, but it's not even infinity, it's just undefined. So questions here with E and F. How's this go? Okay. Very linguistic, right? I mean, I'm trying to keep this unit fairly linguistic, right? It's a lot of being able to understand, okay, if something is negative, there are properties that come with being negative. And if something is negative, I can write that as an equation. That means less than 0. If something is positive, there are properties that come with being positive. And if something is positive, I can write that as an equation, E greater. Right? We're seeing that over and over and over and over and over again, all throughout what we're doing. Which hopefully makes a lot of sense, right? It should be a very intuitive kind of understanding of what these numbers are trying to reflect. And it's nice when we can take intuition and just translate it into the language that we're using. All right, we got about 25 minutes left. That's pretty good. What I want to do, we're going to first and foremost, go here.